Hi, this is Ken, and we're still in our course on mechanics. In this video, we're going to start our study on kinematics on the motion along a straight line or motion in one dimension. And this will be our goals for this lesson. First, we're going to describe straight line motion in terms of velocity and acceleration. Second, we're going to understand straight line motion with constant acceleration. Third, we're going to examine freely falling bodies. And lastly, we're going to analyze straight line motion when the acceleration is not constant. To begin with our lesson, let us have a brief overview first of what mechanics is all about. Mechanics, this is the study of relationships among force, matter, and motion. One branch of mechanics that we're going to study is on kinematics, which is the topic of this video. Kinematics is the part of mechanics that enables us to describe the motion. For example, here, as shown in the figure, we have a bungee jumper that jumps and falls freely from a high bridge. To describe the motion of the bungee jumper, we're going to use later the concepts of kinematics that we are about to learn. In our study of kinematics, we're going to use the particle model, especially in our analysis of motion problems. When we say particle model, we will consider objects like a particle, which is a point-like object, which has mass but infinitesimal size. For example, instead of taking the car as a whole, we are going to model the car as just a point-like object or a particle. Important to our study on kinematics or on mechanics as a whole are reference frames. What are reference frames? When we say reference frames, these are a set of coordinates that can be used to determine positions and velocities of objects in that frame. Consider, for example, you're riding inside a train, a moving train, and then you have a ball in hand. And let's say that you throw the ball upwards, like this one here. Inside the train, where you are at the observer of the ball, of the moving ball, you will see that at later time the ball will just go downwards or fall downwards, like this one here. So the ball travels upward as you throw the ball, and then the ball just goes downward after some time t. This is on the reference of the observer inside the train, or with respect to you inside the train. On the other hand, consider that we have another observer which is outside the train, okay, outside the moving train, meaning maybe someone on the road. While you throw the ball upwards, the observer outside sees that the ball will travel a parabolic path, like this one here, which is quite different with what you saw inside. Now, the observer on the train and the observer at the station are at different reference frames. In this example here, you inside the train, your reference frame is the train, while on the other example, the observer outside the train or at the station is or has the station as his reference frames. So as you can see here, motion is actually relative. It depends on the frame of reference. Another example is, consider for example you have a ball pen on a table. And if you're going to look at the table, or if you're going to look at the ball pen on the table, the ball pen is not in motion, right? With respect to the earth, or with respect to the table, the ball pen is not in motion. However, if we're going to be an observer outside of the earth, or meaning at the space, you will see that the ball pen is rotating with respect to the earth, meaning it rotates with the earth. So as you can see on the second example on the ball pen, the motion of the ball pen is also relative, meaning it depends on the reference frames. The frames of reference we will be using for this course are classical, meaning the effects of special relativity, which is Einstein is known for, are ignored. And also, the frames of reference are inertial, meaning the frames are not accelerating relative to one another. So we have already defined reference frames. In this slide, we're going to discuss on position. The object's position is its location with respect to a chosen reference point. We can always consider the point to be the origin of the coordinate system, like say for example here. Let's say this is the x-axis, and we have a car here moving along the x-axis. We can always define the position of the car by looking at where it is located uh, with respect to our chosen reference point, which is at 0, meaning at the center or at the beginning of our x-axis or the origin of our coordinate system. So we are only interested in the car's translational motion, so we can actually model here the car as a particle. So it doesn't make any big difference if you're going to look at this one as a car, or if we're going to look at this one as a particle. So this is what we are referring to earlier as the particle-like model. So in the next examples, every particle or every object that we're going to study, we're going to look at it as just a particle to make things easier. Now let's discuss your distance and displacement. Are these two terms similar? Let's see. When we say distance, the distance traveled, which you see here in the figure as the dashed line, is measured along the actual path. So looking at the figure here, you see that the particle travels 70 meters east and then goes backward 30 meters west. When we're going to talk about the distance traveled by the particle, it is this actual path here. So that means the distance traveled by the particle is 70 plus 30. Thus, the particle travels 100 meters in distance. Now, what about the displacement of the particle? The displacement, as shown here as the blue line, is how far the object is from its starting point, regardless of how it got there. Meaning, your displacement is just a straight line measured from the origin towards the endpoint, like this one here. Again, regardless of how the particle got from at point 0 up to this point here. Even if the particle moves around in circles or in curves from the origin towards here, your displacement is just a straight line from the origin towards the endpoint. So for this case here, you will see the displacement of your particle is 40 meters east. Another difference of your distance and displacement is that, as you will see, your distance is actually just a scalar quantity, whereas your displacement, this is a vector quantity, meaning it also describes the direction of your particle. The displacement is mathematically defined as the change in position during some time interval. Your displacement is usually represented by a delta x, meaning a change in x. If you're referring to motion along the horizontal or on the x-axis, this can also be along the y or along the z. Along the y, if you're referring to motion along the vertical axis or on the y-axis. So your displacement is represented by the delta x, which is equal to your x2 minus your x1. In some books, you will see that their representation for the displacement is equal to delta x is equal to, you have say x final minus your x initial. So here, when we say 1, this is your initial position, okay, and then 2 for your final position in space. Okay, the SI unit for your displacement is in meters, and your delta x can actually be positive or negative because again, your displacement is a vector quantity. So I would say, for example, here it goes from x1 10 meters, and then the particle travels from x equals 10 to x equals 30. So for this case here, your displacement, you have delta x is equal to 30 meters minus 10 meters. You have delta x, or a displacement of 20 meters positive, so meaning it goes to the east. So you have here a positive displacement. On the next figure, we can see here that the particle started at x equals 30, and then it goes to x equals 10. So calculating the displacement for the particle here, you have delta x equals 10 meters minus 30 meters. Your delta x is equal to negative 20 meters. Meaning here, you have a negative displacement. So again, here you have a positive displacement. Okay, so again, your delta x can either be positive or negative. After talking about distance and displacement, let us talk about average speed and average velocity. When we say speed, this is how far an object travels in a given time. So mathematically, your average speed is just equal to your distance over time. As you will see here, since it is just equal to distance over time, your or our speed is a scalar quantity, just like how distance is a scalar quantity. Your velocity, on the other hand, is the rate at which displacement occurs. It now includes directional information. So your average speed, v, is equal to your delta x over delta t, or your change in displacement over your change in time. Since it now includes directional information, your velocity is a vector quantity. The x here on our formula for your average velocity indicates motion along the x-axis. You can change this one depending on how your particle moves, whether it moves along the horizontal or along the vertical line. The dimension for your speed and then your velocity is in length over time. So that means you're going to use the SI unit, meters per second. By the way, an important note to remember is that the average speed is not the magnitude of the average velocity. Again, the average speed is not the magnitude of the average velocity. For example, we have a runner which ends at her starting point. So meaning, the runner just ends where she started. Like say for example, the starting line is the same as the finish line. So it's like say for example, let me draw. So let's say this is the track. Okay, you have the track here for the runner, and this is where the runner starts, and this is also the same point where the runner finishes. Okay, so you have the same point here. In this case, her displacement is 0. Therefore, her velocity is also 0. Remember that your velocity is a vector quantity. However, the distance traveled is not 0. So the speed is not 0. Of course, the runner runs here, around this oval here. So there is this distance that can be measured, and there is also a speed that can be measured, which is the speed of the runner. However, if you're going to talk about your velocity, since it starts at the same point, okay, it goes around a loop. So her displacement is 0 and her velocity is also 0. Let us have an example. This is about a runner's average velocity. The position of a runner as a function of time is plotted as moving along the x-axis of a coordinate system. During a 3-second time interval, the runner's position changes from x1 equals 50 meters to x2 equals 30.5 meters as shown in the figure. So here, your runner started from x equals 50, she travels to the left, and ends at x equals 30.5 meters. The problem is, what was the runner's average velocity? Again, what was the runner's average velocity? You can pause the video and solve the problem yourself. Okay, let's solve the problem. Here is the solution. So we are given with the following quantities. You have your time interval delta t equals 3.0 seconds, and we have your x1 equals 50 meters, and x2 equals 30.5 meters. Our target is to solve the runner's average velocity. So you have your Vx average. Okay. So your Vx average or your V average is just equal to your delta x over your delta t. So this is just equal to your x2 minus x1 over delta t. Your V average is equal to 30.5 meters minus 50 meters divided by 3 seconds. Using your calculator, we find that your average velocity is equal to negative 6.5 meters per second. We got the negative velocity because, again, your runner here travels from 50 towards your 30.5 and travels to the left or travels to the west. So the negative sign shows where shows the direction of where your runner travels to. Let's have another problem. This is on a distance a cyclist travels. How far can a cyclist travel in 2.5 hours along a straight road if her average velocity is 18 kilometers per hour? In this problem, you're given with the following quantities. You're given with the time 2.5 hours, and you're also given with the average velocity of 18 kilometers per hour. Our target variable is how far, meaning we are asked of the displacement delta x. Now let us solve the problem. Again, your average velocity is equal to your delta x over your delta t. But our target variable is your displacement delta x. So we do some cross multiplication and some algebra. You have your delta x is equal to your V average times your delta t. You just multiply your delta t with your V average here and then your delta x with 1. So your delta x is equal to 18 kilometers per hour times 2.5 hours. You will see that the r units cancel. So your delta x is equal to 45 kilometers. Let us check your understanding. Each of the following 5 automobile trips takes 1 hour. The positive x direction is to the east. 1. Automobile A travels 50 kilometers due west. 2. Automobile B travels 50 kilometers due west. 3. Automobile C travels 60 kilometers due east, then turns around and travels 10 kilometers due west. 4. Automobile D travels 70 kilometers due east. And 5. Automobile E travels 20 kilometers due west, then turns around and travels 20 kilometers due east. These are the problems. Rank the 5 trips in order of average x velocity from most positive to most negative. B. For which trips, if any, have the same average x velocity? And lastly, for which trip, if any, is the average x velocity equal to 0? You're going to answer the following questions in the next video. See you!